In the webinar today, I'll be focusing on a modeling system that we've developed and used over the last couple of decades. That focuses, that is applied towards simulating spills that begin on land, so on-land pipelines, on-land storage facilities, and such. And we use this system to do consequence assessments for various kinds of projects that have various sort of end needs. So I'm going to talk about the motivation for using that model system. So what drives its use? And in that case, we're talking about regulations. We're talking about federal regulations in North America, so the U.S. and Canada, and various regulations in other countries as well. We're talking about those regulations generally for operating pipelines. We also apply the model for permitting for new pipelines or pipeline construction and for sort of general environmental impact assessments. Then I'll move on and talk a little bit about what the models do. So this is not at a technical level. This is at a fairly high conceptual level. We won't get into the technical details of how the models work. And then I'll finish up by showing some examples of where and how the model has been applied. So motivations are, as I said, regulations. So in the U.S., there are federal regulations written into the code, federal regulations, and they have to do with pipeline safety, and in particular, this idea of integrity management, which some of you may be familiar with. So we'll talk in a few minutes about this high consequence area analysis. That's essentially using this model to predict if oil can reach what they call a high consequence area, or an HCA, something like a drinking water well recharge area or a populated area. So that's one of the primary uses for operating pipelines in the U.S. There are also a series of regulations that the United States EPA, Environmental Protection Agency, excuse me, has in place that concern themselves with exposure of oil to inland waters. So those are more along the lines of spill prevention plans, so this so-called SPCC, spill prevention control and countermeasures, and also facility response plans. Those are regulated by the EPA and have slightly different criteria and look at effects of spills from facilities in the U.S. Moving to Canada, the National Energy Board has a whole series of pipeline regulations that are written into the government codes there, as well as documents that spell out the procedures for actually doing these kinds of analyses. So the Canadian Standards Association has some documents specific to those issues. They address pipelines not only in operation but also in design and construction. So the whole gamut of pipeline lifespans are covered under those Canadian regulations. And then lastly, with the increase in North American oil production, crude by rail has become more and more important. It's used to accommodate the high production rates where pipelines can't, and so you see a lot of crude by rail. Right now, there aren't any regulations specifically addressing what the rail companies, the shippers, need to do to address risk or consequences from potential spills that we might apply this modeling system to, but they are likely coming. They just have not caught up yet with the reality of the crude by rail shipments. So in summary, the motivations are federal regulations of various kinds in the U.S. and Canada and other countries, contingency planning that focuses on planning and response issues, particularly for facilities, general environmental permitting for pipeline construction and design issues, and potentially in the future some crude by rail regulations that will address spill consequences for spills from rail. So that's a bit of the motivation. What these models do, we're going to talk about a hazardous liquid spill model that we use, and then also, in a lot of cases, these hazardous liquids are highly volatile, and so there's a large vapor fraction that can be emitted from these spills. So we need to look and see what the concentrations are in the atmosphere. So we have models that address those issues as well. Starting at the beginning, what you need to do, of course, is figure out what the volume is. So if you've got a rupture in a pipeline or a breach in a storage tank, what's the volume that's going to come out and what's the duration of that spill? So we have some tools to do that, and on the left you see a simplified schematic of a pipeline section that shows how the basics of that volume and duration calculation. In essence, we plug in the pipeline operating parameters and the environmental information and the elevation profile along the pipeline, and we calculate volumes that can be released. Interestingly, you can use this analysis tool to help you decide where to place valves and other flow restriction devices, these so-called EFRDs, that can help reduce those volumes that might be spilled in the event of a rupture. So useful for that kind of analysis. We know where the spills are. We need to first determine where the overland pathways are for the spill. So we set up a whole series of spill points. If we're looking at a pipeline, we might space those a kilometer apart along the distance of a pipeline, or we might look at a spill release site from a single location at a facility. The model process, or the model process looks like this. We define a scenario, which is essentially the location of the spill or spills, the volume spilled, the product and all its particulars that are used in the evaporation and other fate process calculations. We also need to define what the environment looks like. So that's primarily land elevation. If we're trying to figure out the overland pathway, we need to know what the elevations are. Land cover is another model input to describe the environment. That defines what covers the land surface. Is it vegetated? Is it desert? Is it ice and snow? Each land cover type has a different holding capacity in terms of the oil that passes over it, and so we use that in the calculations. And then we need to determine or specify a wind speed and also a temperature as inputs to the model to complete the environmental picture. Feed all of those things into the model. We run the simulations, and again, these could be hundreds of individual spill simulations along the length of a line. From that, we get output as spill pathways. So it's essentially a bunch of polygons in a GIS that show for each of those spill locations where is the spill predicted to go over land. So it's an overland pathway. The second bit of output we get is what we call an oil fate summary, or an oil mass balance, that tells us where the oil goes in each of the environmental compartments. Oops, apologize for that, wrong button. So what are the processes that are being simulated in the overland spill model? This little cartoon illustrates those processes in a simple fashion. If we have a rupture, say in a pipeline or in a tank, we have channel flow that we're calculating as the oil moves down slope. We're navigating along the elevation data that we've got in a grid. We have oil adhering to the land surface based on the land cover. We're calculating a rate of retention of that oil. We have pooling. If the oil stream encounters a depression in the land surface, it fills that depression in a pool and may continue on down slope if there's sufficient oil coming in. And we're also calculating a degree of spreading based on the slope and such. Along that whole process, during all of those transport processes and fate processes, we're calculating a loss to the atmosphere through evaporation. So those are the processes, the fate processes, as we call them in the model. In mid-latitude locations, almost always the oil finds its way into a stream or some other surface water feature. So we'll address that in a minute, what happens to that when oil enters a stream. So model outputs from the overland spill model portion. The map on the left is a simple example of what those outputs look like. There's a pipeline running from the upper left to the lower right of that map, and each one of those red circles represents a spill point along that pipeline. So you can see a spill plume or a spill pathway from each of those. They run over land. Some of them enter streams. Looks like a few of them went and oiled a lake. Some of them just simply terminate on land, depending on what the terrain looks like. So that's the output in general. On the right-hand side, those two oil pathways are color-coded according to travel time. So in that case, we're interested in the travel time and the fate of that oil. Useful for contingency planning and deploying equipment and staging equipment and that sort of thing. The second part of the output, as I mentioned before, is the spill time history or oil mass balance. So the graph shows you that time history with the x-axis displaying hours since the beginning of the spill, and then the curves are showing percent of oil that either ended up on the land, was evaporated, ended up in a lake or in a river. And the table simply summarizes all of those quantities at the end of the simulation. So where do we end up? Where does the oil end up at the end of that simulation? So that's a simple example of that oil mass balance result. There are other more complicated things that you can generate and do with that kind of information that comes out of the model. So in the event that the spill does enter the surface water network, what we're doing is we're calculating its transport downstream, or it's spreading across some still body of water like a lake or a reservoir. Those processes or that model looks like this in schematic view. Again, we're defining a scenario. Where does the oil enter the surface water network, and how much volume enters and at what rate? Define the environment. In that case, we need to define the stream network. So we have data that defines a network, stream, river set of features such that if the oil enters any place within that network, we can calculate its downstream pathway from one segment of the stream to another. In that stream network, we define a number of things like stream width and also the velocity or speed of the current within each one of those stream segments. We also define a shore type along those streams and rivers and lakes because the amount of oil that's retained on the shoreline, it depends on the shore type. Each type has a different retention rate. And again, we need to define wind speed and temperature. So we plug all of that into the model, run the simulations maybe for multiple spill sites, and like the land spill model, we get spill pathways defined. So in this case, these are downstream pathways, and then if an oil enters a lake, the spreading of the oil across the surface of the lake. We also get a similar oil fate or oil mass balance output from this model, just like the other model. Processes simulated in the water spill model are, as I mentioned, movement downstream, adherence of the oil to the shoreline, again, based on the different shoreline types, spreading over lakes, and then evaporation is calculated during all of those transport processes. So we're able to track the mass of the oil as it moves through the environment. That output from the surface water portion of the model looks like this example on the map. That's a spill that occurred at that red circle on the right-hand side on the eastern end of that map. You see the downstream pathway and the termination of that spill all the way on the western side in a small lake. In that case, this was an actual spill event that we used our model to hindcast, and so we're trying to do some form of validation of the model in this case to see how well we could do with the different model assumptions and different inputs to the model. And then briefly, as I mentioned earlier, we also can look at vapor transport and dispersion in the atmosphere. So a couple of examples. A map on the upper right shows a concentration, a predicted concentration of, in this case, propane. So that green and black dashed line outlines the area within which there are concentrations of propane that could that cause an explosion if there were an ignition source. So that's within the explosive limits for propane in air. So very useful to be able to make those sorts of predictions under different environmental conditions from different release scenarios. The map in the lower left shows a similar kind of simulation where the colors show the concentration of hydrocarbon vapors from a spill that's making its way down a stream, and so you can see the variability in the release. And this is early on in the simulation, and you're seeing the concentrations of hydrocarbons that are coming off of the evaporative flux of that spill as it moves down the river. So some example applications. We'll just go through a handful of those, showing some results and how the model was applied for different kinds of problems. The most common one, I would say, of the work we do in North America is one similar to what's shown here. And so that map on the screen shows a pipeline that's traced in orange there. There are multiple spills along that line, and the yellow traces show the spill pathways that we've predicted, either over land or downstreams. This was done for a fairly standard HCA analysis, so we want to see if if the model predicts that oil has intersected one of these high consequence areas. So we do a lot of that kind of work. Here's sort of a close-up look of that kind of analysis that we do for high consequence areas. In this case, those blue circles they surround drinking water wells, and so those are well recharge areas. And you can see spill pathways coming off that pipeline running east to west across the map. Some of them are intersecting those HCAs, and in each case, you can determine where the spills come from that intersect a particular HCA. So it points you back to that segment of the pipeline where that spill originated, and it identifies that segment of pipeline as a potential source of an HCA impact. So that's a simple example of how that HCA analysis is performed. Another example comes from tank farm that's located on right next to an estuary. So the image on the left shows you 4 storage tanks, and then in the lower left you can see water in the corner there. That's an estuary. So the question here was, could a rupture of any one of those tanks get to the estuary, and how much time would it take, and what sort of volumes would it take to get to that estuary? We ran some simulations and then looked at the results and then talked to the client about what the results showed, and they said, well, by the way, there's some storm drains around this tank farm property, and it's quite possible that the oil would actually go into the storm drains, go underneath the road that runs along the side of the tank farm, go into a drainage ditch and go straight into the estuary. So sure enough, once we got that information and plugged that into the model, we were able to determine what those pathways were, and we ran a sequence of spills using different volumes and calculated if the oil could in fact get to the estuary and how much oil would be arriving there and what time it would arrive. So an interesting sort of analysis for a tank farm facility. Another example is the Northern Gateway Pipeline, actually pipeline systems. It's 2 pipelines running side by side. The proposal is to build these pipelines to run from Alberta out to the British Columbia coast in order to export crude from Canada. So we did a number of things on this project. We initially, what we did was we modeled over 1,000 different spills that were spaced at a 1 kilometer distance along that proposed pipeline route. And the results from those spill simulations fed into what they called this semi-quantitative risk assessment, or SQRA. And taking those model results, they were plugged into this calculation of a risk score for the pipeline. So the risk score is calculated for each 1 kilometer segment of the line. We plug in a consequence score, which comes primarily from our model outputs, and that consequence is based on if an overland spill plume from a spill point along the line intersects what they're referring to as a high consequence resource, something that is vulnerable to oil, then that gives it a certain score. We plug in that score and we multiply it times the frequency of occurrence to actually calculate a risk score for each kilometer of pipeline. You do that once and you can see where your high risk segments are, and you can go back into the pipeline design process and maybe place a valve along the line or reroute the line around a particular drainage area that might be sensitive water course, and then redo the calculations, rerun the model, recalculate the risk scores, and see how you've improved them. So it's an iterative process where you go through this several times, and it helps you reduce risk along the pipeline. Quite a straightforward form of analysis to do that. And lastly, back to storage tanks for a minute. We have different ways that we've applied the model system to looking at releases from storage tanks. The map on the right is assuming a storage tank is ruptured, but the rate of release is slow enough that the oil simply finds its way downslope and into a river and then flows downstream. A fairly straightforward example versus a catastrophic rupture, where a tank might rupture and oil would flow in all directions. A simple analysis for calculating that is simply to calculate the affected radius, as it's called. So that's more of an engineering calculation, which tells you how far the oil might spread in that catastrophic release. Another way to look at that is a little more sophisticated bit of modeling. In this case, we were looking at the potential of a catastrophic tank failure, and the question was whether or not the oil could breach the retaining wall that surrounded the tank. And so you can see this is a section of a tank. The oil is represented by the blue wedge there, and you can see through a series of snapshots here taken from the animation that, yes, indeed, you would have a problem that a good fraction of the oil volume in this case would just go right over that retaining wall. So this is another way to get at this issue, and it's site-specific. This was run for a particular series of tanks at a location. So those are some of the applications of the model, some different ways we've applied it. Just to summarize in terms of the benefits that we see from using this model system, it is quite good and has been used extensively to meet federal regulations and guidelines for operations of pipelines and facilities, particularly in the U.S. and in Canada, in North America, but also in other countries around the world. Regulations, of course, are different in all different countries, but the end result, the end needs are very similar in terms of what the model can provide. We've also used the model to support permitting for pipeline construction. So there are several large pipeline projects proposed in Canada and other places in the world where this model has been applied to support that permitting process. And we've also used the model for what I would call sort of general environmental impact assessments. And by that, I mean we just run the model and provide some quantitative analysis of the potential consequences from spills. So that feeds into an environmental impact assessment process at a few different levels. That's all I was going to present. I think we have some time for some questions at this point. Karen?
Yeah, and we've already actually had our first question, but just before we get to the Q&A, just in case people have to leave, I wanted to let everybody know that the session was recorded, and we'll send out a recording link shortly. You'll also get a short evaluation, and it just helps us prepare for future webinars to know what kind of upcoming topics you might like. And on the slide is all of Chris's contact details, as well as a list of some upcoming webinars. And feel free, if you don't get a chance to have your question answered now, to email Chris or contact Chris directly. So, yeah, he would love to speak with you about any of these issues. The first question James had typed in the chat pod was, where do we get the GIS data for the water bodies?
Yeah, good question. It really depends on where you are. In the U.S., the USGS, U.S. Geological Survey, provides a very comprehensive set of data for streams and lakes, all surface water, and it's networked and it's very nice to use in the model. Canada has a similar set of data that they provide, not quite as comprehensive, requires a little bit more upfront work to get it in the right shape and form to use in the model. Other places outside of North America, it really depends on whether or not that particular jurisdiction has developed those kinds of data sets. Some have and some haven't. There is a whole range of quality of those data. If there are no data for the place that you're interested in, you can always look at global sources for these data sets. They're comprehensive, certainly, but they are of low resolution typically. They're fairly coarse, both for the stream water network and for elevation data. The things that the model requires as inputs, they're fairly coarse, but they will work in a pinch if you need to. The kind of data we're talking about is all GIS vector data, essentially, for the stream networks. So it's a fairly standard format, typically in some ESRI shapefile or something similar.
Okay, Chris, and I'm not sure if that kind of answers the next question, which is how the geological topology inputted into the model.
Yeah, well, just I'll briefly respond to that, I guess. So what we're defining for the model as inputs is the topography, right? So what the land surface looks like, but also what the land cover consists of. And so those two things define the land for us. The elevation data to define the determine the downslope path of the oil, and then the land cover type to define the oil retention.
Great. And then the next question we had was, when preferably will we do this study? What stage of a project do you see these kind of studies being employed?
Yeah, it ranges. So for operational pipelines and facilities, it can really happen at any time. So it may be a pipeline that's been in operation for many years, and some federal regulations actually require that this analysis is done on a regular basis. So particularly if you make any changes to your pipeline route or operating parameters, you need to run this analysis. For new pipeline construction, we're involved not at the very beginning of the process, but somewhere early in the process, certainly, where they're still working on final designs. So when we got into the Northern Gateway project, for example, they had already done a few preliminary designs, possible routes and pipeline designs. And then we came along and got involved in that process. So it really depends on the kind of project.
And then I've got a couple questions asking about the model software, and is it available for people to run the software themselves, or do they need to hire RPS ASA to be a consultant and run the model for them?
Sure. Yeah, typically can work either way. We provide a lot of modeling services, so we'll run the model for a lot of folks. That's particularly effective if you're not going to be using it a lot, and you may have a one-off project, and it's more efficient for us to do that, to run the model using your input information and then provide you with the results. We do sell the model to pipeline companies and other companies that manage these kinds of facilities. So there's that option as well if you're a pipeline company.
Yeah, and I guess people can follow up with you if they'd like more information on sort of some of those options.
Yep, that's right. So you can just drop me an email and I can provide you with any information you need.
Yeah, and somebody else on that same topic was sort of asking, is it an original software, or does it run inside of another software tool like Argus?
Yeah, ArcGIS. Yeah, it's both actually. So the model is all ours, and we wrote it from scratch, but it is implemented within ArcGIS Desktop. So it's an extension to the ArcGIS Desktop application.
Super. And then someone asked a little earlier on about the type of soil and how it's set into the model. Yeah. I guess they're asking about soil density and
yeah, so at present, the present version of the model doesn't take into account the properties of the soil. So soil type is not considered. Land type is, but not soil type. On the version we're working on currently, on the updates we're making, we are going to incorporate soil parameters so that we can make some estimates of infiltration into the ground itself. So not just collection on vegetation and pooling on the ground surface, but also infiltration into the soil.
Well, that's great. And then has RPS ASA compared, I guess, the model, how accurate it is to real life? I know one of the slides mentioned that earlier, but Chris, can you talk to a bit using the model to compare to what's already happened?
Yeah, so we've done some comparisons to actual spills. I can think of 3 examples within the last year where we've done that. So I did show you one previously that was an example of a spill that went into a river and downstream and terminated in a lake. And then we did another one, which was a spill that remained entirely on land, and it was actually in a fairly developed area, so it ran along streets and, down sidewalks and that kind of thing. And then there was a third one that was another spill that came from a pipeline and ran through a neighborhood, a residential neighborhood, and went through backyards and ended up in a marsh. So in each one of those cases where we collected all the information about those spills, the observations from those spills, and then ran our model and compared our observations, we found that in general, the first time through, the results were not all that satisfactory. But what we did in that first simulation of the spill was we used our standard input data just to see how well we were doing using the standard inputs. By that I mean elevation and land type and all of that. So then we went back a second time and we looked at more site-specific data from each one of those spills. It might have been a revised river flow estimate in the case of the river spill and that kind of thing. We made those changes to the inputs, we reran, and in those cases we got quite good agreement between the model and the observations. So, we learned something there, and I think it's probably something we already knew, was that using the model really depends on how good your input data is and what your results will be.
Right, which is the case, I guess, in most simulations. The better the data in, the better the results at the end. There's a couple more questions come in. Does the model provide infiltration results so that groundwater analysis can be done separately?
Yeah, so right now, that's something that we're working on doing. That version is not available to be used yet, but it's coming. And in that case, we'll determine how much oil actually penetrates, infiltrates into the ground and could potentially impact groundwater. But that's not quite ready.
And I'm not sure quite this last question here. The land spill is modulated in simultaneous when chemicals reach the water.
Yeah. So I guess, I presented how the model works as 2 separate kinds of calculations, or I guess 2 separate models, and they essentially are. One determines the overland flow, and then the other part of the model determines the downstream pathways. They are completely integrated. When you run the model, you don't do 2 separate operations. You run one spill, and it runs both parts of that. The calculations themselves are distinct in the model, but it's one continuous spill simulation in terms of how it's run. So.
And can the model simulate buried gas line releases?
I'm assuming that may mean natural gas, or maybe it's gasoline. I'm not sure. I mean, yes, it is natural gas. Okay. We don't look at natural gas releases per se, other than to predict what atmospheric concentrations might be of various components. So if it's an underground gas pipeline, we don't address that issue where you'd be dealing with things like what's the overburden on the pipeline and what that discharge might look like.
Great. I'll just give us a minute, maybe if anyone has more questions. I think they seem to be slowing down. So again, thanks to everyone for listening and participating. Questions have been great. And again, you'll get a recording as well as a short evaluation. And please visit the website for more details about upcoming ASA webinars. There's also some PEACE webinars that are coming up as well, so lots of information on the PEACE website. And you also have all of Chris's contact details should you want to reach out to Chris directly. So I'm going to end the presentation now, and if anyone wants to ask Chris a question later on, please feel free to do so. Thank you, Chris.
Great. Thank you, everyone.